Now, with this said, stage is yours, Alexander. Thanks already now for your talk. Go ahead.
So let's switch to the laser pointer. Okay, yeah, thank you, Robert, for the introduction. Thank you to all of our participants for joining. Indeed, I will talk about QCL-based spectroscopic ellipsometry today. And there are, I guess, to at least some of you, several phrases to be discussed in detail. QCL, quantum cascade lasers, spectroscopy, infrared spectroscopy, maybe a little bit more in detail, and of course the topic of ellipsometry. So the whole topic I would like to talk is basically the result of a cooperation between the Johannes Kepler University, mainly Christoph Kobert and Kurt Hingel, and RECENT, as Robert already introduced us. RECENT is the abbreviation for Research Center for Non-Destructive Testing. We're located at the university campus in Linz, and we're working in, we're about 40 researchers working in several different research areas, mostly acoustics and optics, and as a member of infrared and Raman spectroscopy, we do develop rather novel measurement methods or act as early adopters of new technologies and potentially combine them to fulfill the needs of industry and science. And this is also where QCL ellipsometry is a part of. So at the very beginning, I would like to start with some basic principles of infrared spectroscopy and the benefits of this method. And this will then lead us to a rather advanced technique, which is infrared ellipsometry. I will explain what this is, how it works, and why and what do we use it for. And those two topics then, which we find out dominated by hardware limitations, and these limitations lead to several drawbacks. And I will then introduce an idea to tackle these limitations, which is then our main topic today, the quantum cascade laser-based spectroscopic ellipsometry. Thus, I will shortly introduce the quantum cascade laser, characterize our setup in detail, and provide some insight on applications. So in infrared spectroscopy, we probe molecular vibrations and phonons. Unlike in the visible range, where we probe electronic excitations, and these molecular vibrations then provide us access to chemical and structural information of the sample. And the way we get this chemical and structural information is typically by the measurement of absorbance or transmittance. So we record spectra of different ranges in our infrared spectral range, and we do look at which specific wavelength radiation is absorbed and at which it is not absorbed but transmitted or reflected from the sample, for example. And the specific wavelength can then be directly assigned to specific molecular bonds, which are then used to identify and investigate the material. And with this measurement scheme, chemical information is not only accessible, it is accessible contactless, label-free in ambient air and room temperature and pressure, basically at laboratory conditions. And with conventional systems, we have access to a very broad spectral range at superior spectral resolution, which is beneficial since a very broad spectral range, of course, allows to monitor a larger variety of different vibrational bands, and makes it easier to distinguish between different elements. And these benefits, of course, lead to a very broad field of applications. For example, surface and particle analysis in a huge number of different fields in industry and science. And one of them is also ellipsometry. And compared to infrared spectroscopy, ellipsometry not only measures the absorption properties of a sample, but the interaction of a sample with polarized light, which means we do not measure just intensity variation through the interaction with the sample, but the change of polarization. So you can imagine that we have our electromagnetic radiation projected onto a sample, and we have polarized light, which means we have a well-defined plane where the electric field oscillates. And the sample interacts with our electromagnetic radiation. Parts of it may be absorbed, there might be interference. And after interaction, we measure the change in polarization, which means we measure a phase difference and an amplitude ratio of two orthogonal polarization states. And this phase difference is typically described by the phase shift delta, and the amplitude ratio is our angle psi. Okay, as you can imagine, there are a lot of different approaches to measure the change in polarization. One can measure in transmission and reflection at normal or oblique incidence, but all of these approaches have in common that one has, of course, radiation source and a detector, and before the sample a so-called polarization state generator, and after the sample a polarization state analyzer, which then leads to this desired information. And such setups provide very unique properties. So they are non-destructive, very sensitive. Ellipsometry is an absolute measurement, which means we measure psi and delta in degrees without the need for any reference measurement. And of course, one can argue now that who is interested in any phase shift or amplitude ratio of a polarization, but this information can be converted to numerous measurable quantities of way more interest. For example, which is ellipsometry, especially known for layer thicknesses with very high precision down to actually sub-nanometer level, depending on the wavelength range. One can measure optical properties like the complex refractive index with just one measurement, both real and imaginary part. One can gather information about crystallinity, anisotropy, surface roughness, dichroism, and in fact, many, many more. And how do we measure ellipsometry spectra? Typically, like also common for infrared spectroscopy, with the so-called Fourier transform infrared spectrometer. Such a device is depicted here on the right. This is not an ellipsometer, but just the spectrometer. And these Fourier transform infrared spectrometers are typically based on Michelson type interferometers, which means one records an interferogram and converts this interferogram to a spectrum with Fourier transform. And therefore, one needs to scan a mirror, which takes a lot of time. And the reason why this approach is still gold standard in laboratories is the fact that these infrared light sources are most commonly thermal infrared emitters. And these thermal emitters come along with several disadvantages. The most important, they feature very, very low spectral brightness, which means low intensity, spread in all directions. And this in turn leads to very long acquisition times to provide spectra with not too much noise, very large spot sizes, limits in standoff measurements, and also when probing highly absorbing samples like aqueous solutions, for example. So the idea is now, of course, to get rid of these thermal emitters and then allow to use a different type of spectrometer, or even maybe get rid of the whole spectrometer itself. And that's actually what we did. We replaced a thermal emitter in a homemade ellipsometry system with a quantum cascade laser. Such a quantum cascade laser is a semiconductor laser made of a very tiny chip of semiconductor heterostructures. The laser itself is also rather small, as you can see in the picture on the bottom here. Still, this tiny laser is outperforming other infrared sources in terms of spectral brightness by orders of magnitude, and also, for example, synchrotron sources, which are like not really compact, of course. Okay, and such a quantum cascade laser is a broadband laser source, but it's not broadband per se. It actually emits monochromatic radiation, but it is spectrally tunable, which means we have narrowband emission, and due to a very sophisticated design of the cavity of the laser, which is depicted here on the left, the laser can be tuned. And this is enabled by the so-called external cavity configuration, which means we have our QCL chip, and one of the cavity mirrors is not a simple mirror, but a tunable grating or a rotatable grating. And the orientation of this grating in the external cavity defines the wavelength which is amplified within the cavity, and thus defines the emitted wavelength. For the applied laser, in our case, the wavelength is tunable from 900 to 1200 wave numbers, which is about 8.3 to 11.1 microns. And this tuning also is very, very fast. So we can tune the whole wavelength range of this laser in the split of a second. For example, 300 something milliseconds. And due to the fact that the radiation is very, very narrow band, we also have superior spectral resolution below 1 wave number. And due to the fact also that we can tune our wavelength, we do not need a spectrometer at all. So we can measure a specific wavelength, which we choose, which are of specific interest, because there might be specific absorption bands, or we can just continuously tune through our spectrum and therefore record our spectrum as a function of time. Okay, that's the light source. And now how does this an ellipsometry setup look like? To exploit the benefits of the quantum cascade laser, we decided to build a so-called phase modulated ellipsometry setup, which is based on a photoelastic modulator. You can see the setup depicted here on the left. We have a QCL, the radiation is redirected with gold mirrors. We have some polarizers just in order to dim the radiation, and then we reduce the beam waste and pass a so-called photoelastic modulator, which is the element shown here. And this photoelastic modulator is basically a zinc selenide plate, which is squeezed and stretched with piezoelectric actuators, and thus it becomes periodically varying birefringent. And this birefringence modulates our polarization state from linear polarized, which is the laser itself, to almost circular polarized, actually elliptically polarized, and everything between. So we have modulated varying polarization, which is projected onto our sample. And all these components here in front do act as our polarization state generator. We generate different polarization states also as a function of time. And the polarization state analyzer is just represented by a simple polarizer here after the sample. And then radiation, the infrared radiation, is then focused on a mercury cadmium telluride detector. So at a specific wavelength, our detector receives a time varying intensity signal. And this variation in the intensity comes from the modulation of our polarization, and different types of polarization on our sample lead to different absorption properties, for example, or interference properties. And this time varying intensity signal on our detector is then pre-processed with log-in amplification, because we are only interested in amplitudes of the intensity variation, which correspond to the frequency, to the modulation frequency of our modulation, which is 37 kilohertz. In fact, we use the first and the second harmonic of these 37 kilohertz, and these signals are then pre-processed, post-processed to our desired ellipsometry parameters psi and delta. There's also an additional signal we acquire by using a simple electronic low-pass filter, which is the DC component of our intensity signal, which also takes part in these equations here and relates to the actual, in this case, transmission intensity. So we do not only measure the intensity, we also measure the change in polarization. In fact, we measure both. Okay, so at each wavelength, we can acquire our psi and delta. And if we then tune our laser, we can also acquire psi and delta spectra. And for our first psi and delta spectra, I would like to show, I would like to demonstrate a comparison to a commercially available infrared ellipsometer from one of the biggest providers, which is Wulem. They provide so-called infrared varying angle spectroscopic ellipsometer. And what we measured here was polypropylene film, so plastic film made out of polypropylene of 6 micron thickness at normal incidence in transmission. And as you can see here in this spectra, we have very significant absorption bands. We have rather weak absorption bands here between those two. And all those bands relate to specific molecular vibrations. And since we measure a normal incidence, we do get additional information compared to classical infrared spectroscopy out of this measurement, which is the anisotropy of the material. We only see these absorption peaks here due to the fact that molecular chains within the polypropylene film are predominantly aligned in a specific direction. And this direction is, for example, a parameter we can measure with this ellipsometry system. So since we see that these peaks are in the positive direction of our spectrum here, we know that these 4 peaks, for example, the 3 prominent ones and the one which is rather weak, they are aligned, for example, vertically according to our setup here, and the 5th weak band here is aligned in the opposite direction, since the sign of this peak is actually negative. We have here the phase shift as well, which is conic consistent to our amplitude ratio. But the very important thing I would like to mention here is that for the red graph, which is our ellipsometry acquired with our ellipsometry instrument, the measurement time was 0.9 seconds, so less than a second. And in order to achieve the same noise performance with the conventional FTIR device, we had to average 300 to 400 spectra, which took almost 60,000 seconds to achieve the same noise performance, which means we have reduced the acquisition time of conventional systems by a factor of about 66,000. And we can also, of course, take a closer look on the noise performance itself by just taking the ratio of 2 acquired spectra, and we will realize then that the signal to noise ratio was improved by a factor of 290. And actually this improvement in signal to noise leads to the possibility to acquire ellipsometric spectra in less than a second. So it was about 16 hours for the conventional system and less than a second for the QCL system. And this fact, in turn, enables the application of this system in a whole new field of potential monitoring of processes. And to demonstrate this, we took the same polypropylene film and stretched it against the predominant aligned molecular direction, which can be shown here in the next graph. We see here the measurement of continuously acquiring ellipsometry spectra during stretching our polymer film. And as you can see here at stage 1, we have our predominant alignment in, let's say, in the vertical direction of our instrument. And then we stretch the film in the opposite direction, and the signal will then increase, as can be shown here, from the transition of dark blue to light blue until almost no anisotropy is present. The orientation of the molecular chains is then almost homogeneously distributed, and if we stretch further, we will see that again anisotropy is introduced, but in this time in the orthogonal direction, the direction along the stretching direction. To demonstrate this in detail, we see a short animation of the stretching process. I will start the video. You can see here our polypropylene film, which is stretched and stretched and stretched just until the film rips. You can see here also how the spectra evolve. Now it started again. We have predominant alignment in one direction. This anisotropy decreases and it's increased in the other direction. Then the film breaks. During this measurement, which was several minutes, we acquired ellipsometry spectra with a time resolution of 1 second. The whole measurement was just limited by the speed of the tensile stage, in fact. Nevertheless, such a monitoring of a dynamic process, in fact, the reorientation of molecular chains within a film would have not been possible with the conventional instrument, since acquiring spectra would just take way too much time. Okay, just for the sake of completeness, we did similar experiments with different types of polymer films. Also, for example, with the PET, polyethylene terephthalate. The result was quite similar. We see a reorientation in our of our molecular chains, but in this time, in this case, yeah, the reorientation was almost so that the orientation of the molecular chains flipped back to the initial state after the rupture of the film, almost, unless there is a specific part of this of the spectrum where this did not happen, where there is modification in the molecular film. However, also these measurements were just realizable by the fact that we could measure within less than 1 second. So compared to the state of the art, we have now realized superior signal to noise, and this leads, in fact, to the very short acquisition times we can realize. Still, there is an improvement we would want to achieve, and this is to reduce the spot sizes. Conventional ellipsometry setups have spot sizes of several millimeters. With the QCL, we had, in this case, already 1.4 millimeters. But we had the idea to introduce microscope objectives, reflective microscope objectives, one of them is refractive here on the bottom, into our setup, and then drastically reduce the spot size of our instrument. As you can see here, this is our setup. The main parts are quite similar. However, before and after the sample, we have a microscope objective to focus our radiation on the sample, and then collimate the beam afterwards to detect it in our detection arm. Additionally, we have introduced with a flip mirror a visible microscope to look out for interesting spots on our sample, and also in order to be able to place our sample here directly in the focal plane of the first objective. And as you can see here on the bottom, with the so-called knife edge method, where we introduced a razor blade from one side to the other in the sample plane, we could calculate the derivative of the intensity signal, which then leads to our beam profile at the sample position. And as expected, we have this kind of redisc shaped beam profile, and we have in this case here a full width half maximum of the first diffraction order of about 8 microns, which should in principle enable diffraction limited ellipsometry measurements. And since we are now able to also like map our sample, the idea is to take hyperspectral ellipsometric images. So for each pixel in an image, we do not have just like a color value, but we do have spectra at each pixel of our image, not only intensity spectra, but also psi and delta spectra. That's the idea behind this. So we then have a huge amount of information about a sample, and due to the fact that we can measure a spectra in less than a second, we can also acquire such images, such hyperspectral data cubes in reasonable timeframes. And to manifest the spatial resolution, we took a so-called US Air Force target, which you can see here on the bottom, just different types of structures on it, and they have a very well-defined dimension. And we mapped such an element of the Air Force target, actually the smallest available in transmission, and we could easily resolve these structures, which were like 35.08 microns apart from each other and also in width. But still, there is, we didn't reach the limit with this measurement, of course, because we could also resolve structures which are smaller, way smaller, as you can see here, for example, this really criterion. And that's in fact what we wanted to demonstrate with the following measurement. We took the security window of a 200-euro banknote, and there are several different structures, metallized structures on different types of polymers. And we could resolve, for example, this 11.8 millimeter gap between two metallized dots. This, for example, is an intensity image. They are very, very close to these two dots. However, we see intensity variations, and this becomes more prominent when we took a look on the psi and delta images, which we acquired just through scanning our sample, and we can easily resolve this 11 micrometer gap. But also we have spectral information at each point of these hyperspectral images, which is shown here on the bottom. We have our psi spectra at a specific point here, and we have our delta spectra at a specific point. And the images, in fact, result from averaging a spectral range of interest in, for example, here where we have an absorption band. Similar measurements were performed on polymer multilayer films, cross sections of such films. For example, we have here polypropylene multilayer in which EVOH, ethylene vinyl alcohol, is introduced as oxygen barrier. And first of all, we can easily resolve this structure in the absorbance image, for example, where we just track on the absorption of EVOH and polypropylene, which is quite different, as you can see on the bottom. But also we can acquire ellipsometry spectra with the same spatial resolution, diffraction limited spatial resolution, in fact. And this leads to additional information again. We now have an idea of how the molecules are oriented within the film. For example, this polypropylene spectrum looks quite comparable to the ones before, but the peaks of the absorption bands show a different orientation. Thus, the molecules are oriented horizontal with respect to our instrument in this case. And in case of the EVOH, for example, we hardly see significant absorption, which relates to that either the EVOH is within this oxygen barrier rather homogeneously distributed, or the orientation of the molecular chains or molecules themselves is like in the plane of the slide in this case. Okay, so finally, to conclude this talk, I hopefully have introduced quantum cascade laser-based ellipsometry. We have realized signal-to-noise ratio, which is improved by a factor of 219 with respect to conventional instruments. Thus, this leads to drastic improvement in acquisition time. We additionally have spatial resolution, which is in the range of the diffraction limit, and this set then leads to complete new possibilities for measuring dynamic processes, and also now at the microscopic level. And the idea is to exploit this new system not only in the scientific field, but also in the industry, and therefore maybe for process control also in production lines. So finally, thank you for your attention. Thanks to all my colleagues in the infrared and Raman spectroscopy group, and also to our funding agencies.
Thank you very much, Alexander, for the talk. At this point, I stopped the recording.